Hello, my name is Emmanuelle, and I'm a volunteer with the Statistics Without Border. Today I'm bringing it to you another lesson on the biostatistics module, more specifically on the statistical computing part of this module. And today what I'm going to talk to you about is machine learning. Machine learning has been a very hot topic for a few years now. I work as a data science, so I use a lot of machine learning on my work. And this concept, those algorithms, they can be used in so many different areas. And today you're going to be learning about how to apply this uh, modules, algorithms, techniques into the biostatistical world. Let's begin then. What is machine learning? Let's start with some concepts before we go into the R part of this module. So machine learning, or ML, is a subset of artificial intelligence, or AI. You can see on this chart here on this that I added at the end of this slide that artificial intelligence was first developed in the 1950s. Of course, it was more of the theory behind, as we did not have the technology that it requires to be what we recognize as artificial intelligence today. So machine learning is a part of this whole big thing, this gigantic thing that we call AI. And the first concepts of machine learning will start to be developed around the 1980s. And in 2010, so pretty recent, 12 years ago, we started what we call deep learning. And but now we're going to be focusing more on the machine learning itself. So we call it machine learning algorithms that can improve automatically through experience and by the use of data. So that means that we are not explicitly programming what the algorithm needs to do. We say that the algorithm is going to learn how to predict something. So that is the entire idea about ML algorithms, that we can make predictions or that we can make decisions from these models. And those models can be used in so many different areas. We can have medicine, we can have email filtering. So when you open your email and you have your spam box, there is what we call email filtering behind that is based on these machine model algorithms, and it's saying, this is likely to be a spam, or this is likely to be a real email. So I'm going to actually display on their inbox users. We can also do speech recognition, computer vision, reinforcement learning. There are so many different applications that we can have with these models. And this is machine learning is not one thing. This chart here, this image kind of shows you the different types of machine learning algorithms that we can have. So we can have what is called supervised learning, that you can see that it then ramificates into regression and classification. And some examples of regressions that we are going to see more in depth later could be, I'm going to estimate life expectancy. I'm going to estimate how much a house is going to be bought for. For classification, we also have some diagnostics, customer retentions, image classification. For example, is this image a cat or a dog, for example? Another class of algorithms, is called unsupervised learning. So from those algorithms, we can do what is called clustering. So we have, I don't know, different users, and we want to see what users have some characteristics in common. So we might cluster those users by those common characteristics. And this way we can recommend. So maybe I know you like a particular show. I'm gonna recommend you a similar show, maybe by genre or by what your friends like, for example. And we can also have what is called dimensionality reduction. That is, imagine that you're working with, I don't know, DNA, genes. So you have hundreds of thousands of columns in a data frame to represent one single gene, one single strain of the DNA, for example. So it's very, very difficult to work with all that amount of columns. And most of the algorithms we have, it's what we call, you need to have more rows than columns. And a lot of times that's not really possible. So can we reduce that information into smaller variables, but still retain most of the knowledge that all those columns are giving me? And the latest part of machine learning algorithms, the latest type of algorithms, is what we call reinforcement learning. So reinforcement learning can be used for games. Maybe you've heard before of computer games that have beat humans in chess or in any other video game, for example. And usually the algorithms that are behind that are what we call these reinforcement learning kind of algorithms. I just gave you a very briefly overview of all the different types of machine learning algorithms. But now let's dive deep into each one of them so we can actually understand what kind of problems there are, how to use those algorithms to solve problems that we might have in the future. So let's go. I'm going to start talking about supervised learning. The reason I decided to start with supervised learning is because this is the most common type of machine learning problems. And it's called supervised because you're usually going to have a label or the output variable. So this label, what it tells us is the correct information. So imagine that you have, for example, a user and you have their weight, their height, and some blood samples from exams that the user has done, and you want to predict if that user has diabetes or no. But you have that information already on your data set, so you know if the person is sick or it's diabetic or not. And so this is diabetic is what we called our label or our response. And then based on all the other variables, we want to be able to predict if that user has diabetes or not. So that's why we say that in supervising learning, we have input variables X and our output variable Y, and we want to create an algorithm that's going to learn how to map the input to the output. So you pretty much have a function of Y that receives X as their dependable variables. And by having the correct classification, the correct information, we can pretty much we can learn when we are training the algorithm. We're gonna have the algorithm's gonna start by, I don't know, maybe random guessing, yes or no, yes or no. And then it's gonna always check the correct label and see, I was wrong. So I need to learn something else. I need to pretty much update my weights, for example, and say, okay, now I'm actually right. And then when you go to the other users, I'm wrong. And then by having that correct information, the model can update its weights and better understand what are the relationships of your dependent with the independent variable. And eventually, we can use another subset of the data to predict ignoring the classification. And then we are gonna compare the prediction with the actual values and see how wrong or how right we were. And ideally, we want to be as closer to 100% of the times being correct. And Supervised learning, it can be grouped into two types of problems. It could be clustering, it could be classification, sorry. And that's what I've been talking to you about. So you have a category, so disease or no disease, diabetes or no diabetes, cats versus dogs, anything like that, anything that can be a category. Or you can have what we call the regression. The main difference of classification and regression is that in classification, your response variable is going to be a category, but in regression, your output variable is going to be a real number, for example, weight, or if you want to predict the price of a house, you might have, I don't know, number of bedrooms, number of bathrooms, if there's a garage or not, all of that as the variables, as the features. And you want to actually predict the price, and that would be your label, your target. That's your output variable, right? So in here we don't have in this case we don't really have kind of a number of rights or wrong, but in here we're gonna have the difference. How far away are we from the truth? So if a price is 10 and I say that it's 9, then I am uh, 1 pound, $1 away from it. But if I'm saying it's 9.99, then I'm actually a lot closer. So that's how we understand how good our model is for that kind of problem. But again, we're going to see this in more depth. So when you're doing a supervised learning kind of problem, you have a few steps that you usually have to follow. So we start by data collection. Sometimes you're gonna have the data already because someone collected for you. Well, other times you need to go yourself after the data. So that is usually the first step. And in the data collection, we have also checking that the data is collected properly. Data quality is something essential. There is a very important theorem in machine learning that says garbage in, garbage out, which means if your data is bad, your response, your model is gonna be bad as well because it's learning from garbage, so not good. So always make sure that your data is correct, clean your data, make sure there are no outliers, all that. The second step would be exploratory data analysis or EDA. That's where we try to understand how the data looks like, the patterns, shapes, the distribution of each of the variables and the variables together as well. Then we would go to a data processing, or there's also feature engineering where you're gonna maybe check which features you have. Do I have features that are correlated and then I need to remove one of them? For example, I have minimum temperature, maximum temperature, and difference in temperature. You don't need all three of them, right? Because with min and max, you can get the difference. And also, if you keep max and difference, you can also get the mean. So that kind of variable, it's to keep all three variables kind of unnecessary for the model. You're going to make things more complex when you don't need to. And the final step would be the data modeling. That's where you're going to actually apply the model and check the performance of your model. I'm going to briefly explain each of these steps next, and hopefully that will be clarified when we have the example. So let's see with more details each one of these steps before we actually see the examples. So data collection, very, very, very essential step for building a machine learning model. Again, the model will learn from the data set you've provided. So garbage in, garbage out, that's very important. Collecting, cleaning, and manage your data properly is a key factor for any machine learning project. we, as data science, we usually say that we spent 80% of the time on this step, on the cleaning, collection, managing of the data, and the other 20% of the time is where we are actually manipulating the data by doing exploratory data analysis or data modeling. It's not the fun part, but again, it's super important, and you always need to make sure that you're doing it. So the next step is the EDA, exploratory data analysis, to understand characteristics, the distribution of your data. So by understanding the data beforehand, we can already have some sort of feeling of what kind of model and most importantly, what kind of the type of learning that we are dealing with. Because we're going to see there, I have a classification here, or I have a real number, so I'm actually dealing with a regression. So very important step as well. Then we go to the data processing, that it's a process of cleaning the data and enabling them in the right format. So checking for missing values, doing feature selection, feature engineering, sorry. If the data set is not good and if there are missing values, outliers, or the features are not presented in the correct format, the ML model that you're going to build from this data will probably be bad. So we can have some methods here that we used in this pre-processing part, that it's called encoding, normalization, imputation, outliers, and an A, it's not a number, rejections, and feature selection. So to explain that a little bit more, encoding, for example, is a method that we transform categorical data into numbers. And why we do that? Because some models cannot understand the words, they need numbers. Other models are going to be a little bit more smart, but maybe because the language. So R, a bunch of packages in R, even though you have, for example, categories cat and dog, behind the curtains, it is seeing it as a number already, so you don't need to transform to actually encode it to a number. But other times that's not possible, that doesn't happen, so you need to actually go there and say, so cat, for example, is going to be 0 and dog's going to be 1. If you have more, then you can give different numbers, or what you can do as well, so for example, if you have cat, dog, and bird, it can be 0, 1, and 2. Another thing that you can do is called one-hot encoding. So everything's going to be zeros and ones, but then, for example, uh, each classification is going to be a column. So you're going to have only cat and dog, and you're going to remove the birds, because if cat and dog are both 0, you know that the classification is actually the other one, the one remaining, that would be bird. So you're going to have everything as zeros and ones, but now they become columns with one less class. Another thing that we need to do is feature scaling. Some machine learning models, they are gonna be affected by different ranges, and those different ranges are gonna add bias to your model. So for example, if you have height, you have someone that has 150 centimeter height and the salary is 40,000 something. So salary in the model might say that salary is a lot more important than height, just because it's a big number. Uh, but that might not be true. Actually, height could be better, but the model is gonna hide that information just because the difference in ranges. So that's why we need to transform the numerical values to the same range. So there are a few methods that we could do that. One of them is what we call min-max normalization, or just normalization, which means that we are scaling everything to a new range between 0 and 1, and this is the formula. So you have the values minus the minimum number of all the values for that particular feature, where features are columns as well. This is a feature is the most common way of calling a column in machine learning, and then you're going to divide that by the maximum number you see there minus the minimum number. This way, you're always guaranteeing that everything in that particular feature is normalized between 0 and 1. So you do the normalization per feature, not every feature together. So you're not going to do, for example, 150 minus 40,000 for the salary, because then you're going to mix the features together, and that's not the idea. The other method is standardization or z-score normalization, which means that we're gonna create this new range with a zero mean and a standard deviation of 1. That's why it's called z-scores, based on the normal distribution with mean 0, standard deviation 1. So what we're doing is really that we're gonna take the value minus the mean of the feature and divided by the standard deviation of that feature. Again, you do that per feature, not per observation, always per column. The other thing that we need to do is check for missing values. So when we have missing data, it means that the data is not available. So we have missing information. So we can deal with that in different ways. We can remove the missing data if we have enough data available. So if you have a data set with 10 rows and 2 of them or 1 of them has missing information, you're not going to remove that, because then you're going to be left with only 9. And that's not enough to train and test a machine learning model. So you need to have enough data to decide to remove that data. And you can only remove that missing data if there is no pattern to it, which means that these missing values are random. But if you start seeing, for example, that, I don't know, everyone that has red hair like me doesn't have the height information, then there's definitely a pattern there, and you shouldn't remove that missing data. Another thing that you can do is imputation. Imputation means that we are going to input the missing data using some sort of statistical method. So we can, for example, use the mean or median of the feature to input missing values. So, for example, we have that for everyone that we have their favorite color, and every girl, for example, likes red. So we might input, if there is someone that says that they are a girl, we can say that their favorite color is red, if that information is missing, for example, if that makes sense. But you can also apply some algorithm, for example, a linear or logistic regression to determine the possible, the likely value of that missing value to be. So you're missing some weights information, but you have everything else. You have age, you have BMI, I don't know, you have everything. And then you might think about, I'm gonna actually apply a linear regression here and see what the value for that missing value would be. And then you can do that. But then it would be a two-steps model, right? The first model would be to do this imputation, and then your final model to actually do the predictions. So you have some options there. And the last part would be feature selection. So it's very important for us to select the most relevant variables for the model, because we can simplify the model. If we have a lot of variables, the model is going to be very complex. And the more complex you make the model, the more difficult it will be to generalize something. And the whole idea of machine learning is to be able to predict, right? So we need to generalize. On unseen data, we train on known data with the values, with the targets that we know to be true. But then it doesn't matter if we can predict what we know or not, right? We already have the result. That's not very useful. So that's why we say that the whole idea of machine learning is to be able to generalize on unseen data. So what if someone new comes to my data set? Can I rightfully predict what what their classification, what their value is going to be. And that's why the more complex the model is, the more difficult it is to generalize. And this way we have what's called overfitting. Overfitting is when your model doesn't generalize, your model doesn't learn anything. It pretty much knows how to connect the dots. I know that this is what I need to do. But then when someone new comes, it doesn't know how to connect that dot. So we overfit it. And that's not the ideal. And again, if you have less variables, you also have less training time, which is always good because training, you spend money, you spend time on it, and the little time you can spend on that, the better could be for you for other reasons. And the last step that we have is the data modeling. So for the data modeling, we have some steps within it. The first one is splitting the data. What do I mean by splitting the data? So before we apply any model, we need to make sure that we have a data set that we are going to train and that we are going to evaluate the model. And another one that we are going to test the accuracy, the performance of the model. Because as I just said, we need to make the model learn and generalize on unseen data. So if you use the same data set for training and for checking your performance, or what is called testing, we are leaking information to the model. So the model pretty much knows what to expect from that test data because it saw it already. So if you're overfitting, you might already know what is the pattern. And this way we can guarantee that the model can generalize. That's why we need to have two distinct training and test data sets that will help us with overfitting and underfitting. So I've been telling you about overfitting, and underfitting is the opposite of it. It's when we don't learn anything. We have the data there, we leave it training for however many hours, however many minutes, and in the end the model learns nothing. When we check, when we compare, it's just terrible. So this is underfitting, and overfit. It's when it's pretty perfect your training set. You can see, you can understand if you're overfitting because you're gonna do the performance of your model when you're training, and it's gonna be amazing, 90% over. But when you see your test set is terrible, so you can say that your model overfitted. So again, always split the data, and the splits are usually training, validation, and testing. And this split could be usually be done as 80% for training, 10% for validation, 10% for testing. You can also do 70% for training, 15 for validation, 15 for test. A very important step not to be missed. So the training set, just to explain you a little bit more what each of those sets do, the training set is the data that we are actually going to use to train the model and to make the model learn the features and the patterns in the data. So the training set, as I mentioned before, is either 80 or 70% because it has to be large enough so the model can learn correctly. It will be the largest set of all of your sets. And most of the data that you have available is used for training, again, because we want the model to learn. And to learn, you need to show the model a lot of different examples. The next set that we have is the validation. The validation set is used to help us validate our model performance during training. So we train the model, we have there the weights, and then we can apply that model to the validation and see how it performs. But if the model is not that well, it's not that good, we can use it to tune the model and configure it accordingly. Every model has what is called hyperparameters that will be trained, that will be uh, best tuned during this validation time. So in the end, what the validation set does, it's really tell us if the training is moving in the right direction or not. And the whole idea of having this validation set is to prevent our model from overfitting. So again, the model becomes really good at classifying the samples at the training set, but it cannot generalize or make accurate classifications on the data that it hasn't seen before. And the last set that we have is the test set. So once you finish the training, you check the performance of your model, by using metrics like accuracy, precision. You have all that, you're happy with that. The validation also tells you, hey, your model is good, it's going on the right direction. So you need to apply the model on this test set, that is the data that it has never seen before, and we check the performance of the model there. The performance of the model on the test set is pretty important. It's gonna answer the question, how well does my model perform? So it's pretty important to have that split on your data set. The next step, once you split the model, would be actually modeling and evaluating the model. So there are a bunch of machine learning models that you can choose according to your objective. So you can use linear regression, logistic regression, support vector machines, SVMs, decision tree, neural networks, so many different models that you can use. We are going to see some of them as we go through the examples. Once you train the model, you need to actually evaluate it by checking the performance. So it depends if you're using a supervised or unsupervised learning, if you're using a classification or a regression type of model. But we have different metrics to check how good your model is, and now I'm gonna only focus on the supervised learning ones. So for classification, you have what we call F1 score, precision, recall, accuracy, confusion matrix. We're gonna see all of them in more detail as we go through the example. And for the regression metrics, we have mean absolute error, mean squared error, root mean square error, the R2 metric, that again, we're going to see them being used as we go through the examples. And the final step is the prediction. That is, you're going to apply and you're going to predict, once you train your model, you're going to apply this model to the samples on your testing set. And once you're happy, that's it. So let's start with regression. Now we're going to start diving deeper into each one of these different supervised learning models types by showing you the examples. You've been waiting for this moment, the examples in R. So to starting with regression. Regression is a type of supervised learning algorithm, as you know that by now, and is the kind of algorithm that can be solved, for example, with a linear regression. Because, and yes, it is the same linear regression that you've previously seen in other modules. Uh, in general, ML doesn't make any assumptions, but the user should make sure that the data meet the assumptions of the linear regression model if they want to use it. So I say that because in machine learning, we're more interested about how well your model is gonna predict something. So if it meets any of the assumptions or not, it's not that important as long as it's predicting well. But again, it's up to you to make sure. And I would definitely encourage to always do those checkings before applying the any kind of models. So to explain how we solve a regression problem, I'm gonna use as example the medical insurance costs dataset. This data contains medical information and costs billed by health insurance companies. It contains 1,338 rows of data, and we have the following columns: age, gender, BMI, children, smoker, region as features. So those are our X variables. And we have the insurance charges as the label or as the Y variable. For this example, I'm going to use the tidyverse and tidymodels libraries from R. And tidymodel, is a library for machine learning workflows in R that follows the same language as the tidyverse one. So they go along very well together. So just the example. So let's start. The first step was data collection. So the first step, collect the data. I got this data at a GitHub link. It is available there. You can see on the example here that I am first loading the libraries that I'm going to use. So tidyverse and tidymodels using the library function from base R. And then this is the GitHub URL where you can see the data that I'm using. And you can just read the CSV because that data is a CSV, as you can see here at the end of the URL.csv file. So you can just use the read CSV from the one of the tidyverse libraries, passing as argument the URL. I'm going to use the glimpse function that's already loaded with those libraries, so we can just check the how our data looks like. So it gives us some idea of showing us all the columns and some of the types that are things those variables are. So for example, age was read as a double, sex as a character, BMI also as a double, charts, that is our Y variable, as a double. We can see here that we have smoke and region that are just like sex, some factors, but they were read as characters. So this is how the data looks like. So I'm gonna do a very simple EDA here. I encourage you to spend a long time doing this step, but just for the example, I'm not going to spend that long on this. So I'm going to be using the package dlooker to help us with this step. In this package, you can use the function describe. And I'm also using the library DT just to present this nice table to you that you can see is an HTML. I can move, so it's pretty nice. So from the dlooker, I'm using the describe function. So I'm giving the data set that is called insurance, as you saw here that I called insurance. I'm gonna give also some quantiles that I'm interested at. So 0 that represents the minimum, 25 that is the first quartile, 50 that is the second or the median, 75 the third quartile, and 1 that represents the maximum value for the features. And the statistics also that I want to show, there are very different statistics that you can choose. If you go to the helper of the package, you can see all of them that are available. I just picked a few here. So I picked the NA that gives me the number of NA values or missing values, the mean, the standard deviation, the interquartile range, and the actual quantiles here, so that I need to say that I want the quantiles to actually have those here that I initially asked for. And then here I'm just displaying the data table in a nice format. So this, it's going to give me the values for the variables that are considered to be numbers, that are the ones here as doubles. So for example, the sex, smoker, region are not going to be here because they are not numbers, so I cannot really get a mean, a standard deviation, or anything like that. So we can see that we have all the variables are populated. We don't have any missing values, which is pretty good. We have here the mean for each of the features. We can see that charts, for example, you can see the importance here of the scaling, because you can see that they are all in very different ranges. Look at those charts. They're gigantic numbers compared to number of children, for example. We have the standard deviation, the IQR, and the minimum values here. So, for example, for children, the minimum number of children that people had is no kids, and the maximum was 5 kids. So this is just a very quick descriptive analysis of the data set. Now we can go we can also show these descriptive values per each of the factors for each of the categorical values. So for example, by sex, I'm displaying the same information, the same statistics. The only difference is that I'm actually grouping by sex beforehand. And then we have here the age, children, all of that per sex. We can see that they are, we don't have missing values. We don't have any. We can see the differences per each of the sex variables, sex classifications, that we only have 2. So that's why we have only 2 repetitions for each of the described variables. You can also have the same by smoker, the smoker classification. The same for region, that we have here a lot more. We have 4 regions actually, and you can do also a correlation. That's the final thing that I've done. Once I've done all the descriptive analysis, I decided to do a correlation of all the variables, just to understand if there are variables that are highly correlated between them, and then I would remove those variables from my data. So we can see that none of the variables here are considered to be highly correlated. They're all pretty much around 0. The most correlated ones are charges and age, which kind of makes sense, right? We know that the older people get, the more expensive the charges of healthcare gets. So this is my EDA, and again, I encourage you to spend more time doing this step. Spend as much time as you want, but this is an example, and the actual juicy part is the machine learning models. So now that we finished the EDA step, we can go to the next step, that is the feature engineering, feature selection, all that. So first, we saw on the glimpse that the character variables that we had were not converted to factors when they should be factors. So sex, we have only a limit number of options. Smoker is always either yes or no. Region are one of the 4 possible ones. So they should honestly be characterized as factors, not as characters. So this is the first thing we are gonna do here. We are gonna transform the character values to factors by using the mutate if function. So what this function does is we're gonna mutate, we're gonna alter the variable if a condition is met. So what I'm saying is, if my variable is a character, the mutation, the transformation that I'm gonna apply is the S factor function. So then if we see the glimpse, now all the characters became factors. Uh, we are not gonna do the range. We're not gonna change the range of the numeric variables, because ordinary least squares kind of models, like the linear regression one, they are invariant to the scale of numeric variables. So you don't need to transform because the difference in ranges are not going to have an impact on how the variables are going to be used by the model. But other methods like lasso or ridge regression, they are not invariant. Sorry. So before using those models, you need to change the ranges of your numeric variables by applying some min-max or z-score normalization. So again, for invariant methods, there's no real need for standardization. For non-invariant methods, you should standardize. So always check if your model needs that or not before applying the model. So you are aware of the feature engineering process that you need to apply to your data. So as we don't need it, I am not gonna do the standardization of the numeric variables. And what I'm gonna do is I'm gonna already step on to the next step on the steps of applying a machine supervised learning machine learning kind of model. So the next step is the data splitting. So the function that I'm gonna be used is the initial split. That is a function that is already going to partition the data for you into training and test sets. This function has two main arguments: the data, that is the data set you want to apply this split, and the proportion. So, and the proportion is going to be a number between 0 and 1. So for the example, I'm gonna do a 80-20 split for training and test. So I'm gonna, so you can see here, first of all, you always set the seed to ensure that your results are reproducible. If you don't set the seed, you're gonna have, anytime you run this example, you would have different splits probably. So maybe row 1 was in the train test, or was on the train set, but next time you run it might be on the test set. So you might not necessarily get the same results as I will on when you do the example by yourselves. So that's why I'm setting the scene, and again, reproducibility is very important. So I recommend to always set the scene when running any model. So you can create the split object. To create the split object, I will use that function that I mentioned at the start, the initial split. So I pass here the data set insurance and the proportion 0.8 because I want an 80-20 training test split. So to build a training set, we need to apply another function. So what we do is we apply the result, so the split, and we apply the training function to it. And we can give a variable to that split. That's going to be the train part. So always apply the training function to the split, and we can see here the dimensions. I'm printing that information. I have 1,000 rows and 7 columns, so the columns should be the same. The only thing we split is the observations, the number of rows, not the columns. And the test data, so if I apply the training function to the split to generate the train variable, to generate the test variable, I'm gonna apply the testing function to the split. So I'm using pipes here, but it would be the same to do testing brackets insurance split uh, inside the brackets, because this is what the pipe does. It's just saying that I'm putting the insurance split inside the testing. I'm applying the function to what comes to the split. And you can see here the dimensions. I have 268 rows and 7 columns. Again, the number of columns should be the same, and because the split happens only on the rows. So if we move forward, since we have those splits already, we have the data set that I'm gonna use for training, and I have the data set that I'm gonna use for testing, I can actually start thinking about the model that I'm going to apply. So as we mentioned at the start, when we start talking about regression, I'm going to build a linear regression model to fit our training data. So for every model type, for example, linear regression, we have so many R packages or what we call engines that can be used. For example, LM function is a base R function, so that is already inbuilt. You don't need to install any library to have access to that function. But if you want to use, so LM is what we call an engine that will do a linear regression for you. But you can also have a linear regression from other packages. So for example, you can want to use the stun GLM function that comes from the RSTANNRM package. Uh, but then for that, you need to actually install the package first before you have access to the function. But in the end, both of these functions will fit a linear regression model. But the way that they implement the linear regression is going to be different. So that's why there are different functions with different engines. We have a package that helps us with the tidy models that's called Parsnip. This package, it acts like an aggregator across all the different engines that we have in R. So it makes it a lot easier to implement machine learning algorithms from different R packages using one standard syntax, which is very powerful, right? Because each engine is going to have its own way to call the model, call the function, apply, summarize things. But using Parsnip, you have a standard way of doing everything, and usually it won't matter which engine we want as long as the engine is recognized by the Parsnip package. So to specify a model with Parsnip, we need to pick the model, that is linear regression, set the engine, so choose from where we want the implementation from, and then set the mode, where the mode for supervised learning is going to be regression or classification. So let's do that. So let's start. We have the linear regression. So that's how we pick the model. The first part, pick a model. In Parsnip, the linear regression one is called linear reg. So you're saying, I want a linear regression model. And now we need to actually set the engine. So if you can see here, I'm applying with the pipe the engine that I want. I'm going to use the base R engine LM. So this is why I'm writing LM. So I'm adding the LM implementation of linear regression. And then I'm going to set the mode that is a regression type of model. So if you run this, if you type this to see the model, you're gonna see that it's you're gonna see the properties of the object. You're just gonna see that it's a linear regression model. That's what we define. Uh, the specification here is regression. That's the mode here, and it tells you also the computation engine that you chose. That is the LM base R LM. So when you see the properties, everything is in line with what we define here as code. So the next step is to actually fit the model to the data. So to do that, we are going to use the function fit from Parsnip as well. And this function has the following main arguments. It requires a Parsnip model that we already run. It's our LM model. It needs the module formula, just like you've done before on your linear regression model. You need to give the formula. So for example, charges is our Y variable. And to give formulas in R, you use the tilde as a kind of separator of what is the Y and then what comes the X variables. So we're saying here that the Y is charges and the X variables are gonna be everything, all the other variables. That's why we use the dot. So, and that dot then is representing age, sex, BMI, children, smoker, and region as the predictor variables. and you need to pass the data frame that you're using with the training data. So you can see here that the data is insurance train, because again, we train the model with the train set, not with the test set. And you can see the properties of the model. It has here, see, it's an LM, charges. This is just the intercept, everything that you're gonna get if you just see the summary of the model, for example. Then I feed the model. It has a lot of information here. That's why it's cutting a lot. But on the next page, you're gonna see the actual summary with the coefficients in a more clean way. So we can use the broom package. And we can use the functions tidy and glance from the broom package, because those functions, with the broom they kind of clean things. So the idea is to show the same thing, that by calling the model, the result of the model itself, that it's a bunch of text in a more clean, easy to look at way. So if we look at the tidy function here, if we apply the lm fit, so the model train on our training data, and apply the tidy function, what it's gonna give it to you is the estimated model coefficients, their associated F statistics, and the p-values. So we can see here the intercept, age, sex, it's using male as reference, BMI, children, smoker, yes, and here the regions that and it's using a one hot encode, so that's why you only see one and not two, so not smoker, yes and no, sex, male or female, because you can just when it's female, this will be the you can do the calculation, you can get the results from that by just having the male. So you can see here the p-values, the statistics, everything you need to know about your model. But then you can also want to know the performance metrics. That is the most important part here, right? We want the performance because we want to know how well we're doing when we're predicting things. So we can use the glance function from Broom. It's gonna give you a lot of the performance metrics of the model. So you can have here the R square is 76, 75%. There's also the adjusted R square. We have some statistics, the p-value, the degrees of freedom. So those two metrics here are going to help you understand the performance of your model. So once you train the model, you actually apply the model to your test data, to your test set. So we can do that by using the predict function that has two important arguments, very important arguments. That is the trained model and the new data, so the test set that you actually want to generate predictions for. We can put everything into one single data frame so we can compare better. So you can see here I'm getting the results. This is the insurance test results. I'm creating a new data frame where I'm doing the prediction. You see here, this is the model that we just trained, and this is the new data that I want to predict, so the insurance test, and I'm just binding the column, binding a console, adding the columns to the initial insurance test data. So you can see here that what you've done is adding the prediction column to the insurance test as predict. We can see from this example here that we are pretty far away, right? 3,000 against 21,000. Not very good. But now what we can actually do is to evaluate the model to see how good it was. To evaluate the model, I'm going to use RMSE and R2 that are obtained by using the functions RMSE and R square. So both functions take the same arguments. You need the data frame with the real and predicted values. That is the one that we just created, the insurance test results. You need the truth. That is the column with the real labels. That is what's called charges. And you need the estimate. That is the column that has the predictions, that is the dot bread column. So I'm just binding the rows here just so we can see them together. You can see that the RMSE is 7,000, the R squared is 0.7. The close to zero the RMSE value is, the better your model is, because it means that what the RMSE is doing is saying, okay, I predict something to be 3,000, but it's actually 21,000. So I'm gonna do, for example, 21 minus 3,000 and take the square root and take the squared, right? So everything's positive, and you do 3,500 minus 3,700, and you're gonna do the sum of all those square differences and then take the root square from it. So that's what it's called, root mean square. And you're gonna do the average of all that as well. That's why it's the root mean squared error, because you're gonna do, the error is the difference. The squared part from the error is because you're squaring everything. You take the average, so you're gonna divide all that by the amount of observations you have, and then you apply the square root to it. And that's what this value is telling you. So that's why you want the closest to zero as possible, because it means that your predictions are pretty close to reality. The further away it is, it means that your model is not a very good model. We can see that 7,000. This is gonna depend on the work you're doing, on the actual project that you are, but 7,000, as this is price of health insurance, to say that you're erring by 7,000, that's quite a lot of money. But if it was maybe something else, it wouldn't be that bad. So you always need to be aware of the context that you're inserted as well. And that's how you evaluate a regression model. So this, you can also plot the R2, for example, if you want to visualize the errors. You can see that the predicted values actually for uh, the insurance that are cheaper, we are a lot more in line. But when we get to more expensive insurance values, we're pretty far away. And of course, the more expensive it is, the biggest the error is going to be if we are saying that it's cheaper. So this is how we can visualize the predicted versus actual values. And this pretty much finishes how you deal with a regression type of problem. And now we can move on to classification. We saw that there are two types of supervised learning: regression that we just seen, and now classification that we're going to see more in depth with some examples. So classification is a type of supervised learning, and we categorize data into classes. That's why we're saying that we're classifying things, and it's a classification problem. And there are many different algorithms that can help us solve these kind of problems. Classification requires a training data set with many examples of inputs and outputs so so the model can learn. And we can have two main types of problems within classification. That is binary classification, when the outcome has two labels. So disease and not disease, or dead and not dead. Some popular algorithms that can help us are logistic regression, decision trees, and KNNs, k-nearest neighbors. We can also have multi-label classification, and that is when the outcome has more than two labels. So it has multiple labels. For example, dog, cat, bird, other. Some popular algorithms that help us are KNNs, decision trees, random forest, and naive Bayes. So to evaluate the model performance, we can make use of raw curves, confusion matrix, etc. So you may have noticed that those are different names than the ones that we were using for regression. And why is that? Because regression is an actual number, the outcome. So we can compare the value that we're predicting with the actual value by, I don't know, like the RMSE. We're taking one from the other, squaring, taking averages, adding root square. So we can see the actual difference, the numerical difference of what we predicted to what the reality is. But in here, as it's a class, it's either you got it right or not. So we need metrics that help us have that understanding of is it correct or not. Now it's pretty much a Boolean, the answer here. And we need to be aware of what we call class imbalance problems. This is the most common type of problems when dealing with classification. So the evaluation metrics, as I said, they have to be a little different from when we are dealing with regressions. We have some common metrics that are accuracy, precision, recall, ROC. They're all very common names when we're talking about evaluation in classification. And most of these metrics can be determined by creating a confusion matrix. Confusion matrix is this image here that I'm showing you on the right side of this slide. It pretty much is a contingency table with two dimensions, the actual, so the actual real value, and predicted, the value you're predicting. And that helps us determine the performance of a classification model when we know the true classification of the data. So we can see here that we have for both actual and predicted negative and positive. And those are just the name of the classes, but it could be 0 and 1, dead, not dead, disease, not disease. It could be anything. But positive and negative is kind of the standard of how we represent confusion matrix. So you can also see here that we have, for example, true negatives, true positives, false positives, and false negatives. What is that? So true positive, it means that the model said that it's positive, and in reality, it is positive. So I predicted that someone has a disease, and they actually have that disease. So this is a true positive. But a true negative, on the other, it's the opposite of that, is when something is truly a negative classification. So I said, my model said that that person's not sick, they don't have the disease, and in reality, that person does not have the disease. We can also have false positives, or what we call the type 1 error. False positives are when we're saying that someone is sick, so my model said that person is sick, but in reality they're not. And the false negative is the opposite of that. So I'm saying that someone is fine, they're healthy, they don't have the disease, but actually they do. And that is also called type 2 error. So from the confusion matrix, we can get a lot of evaluation metrics. The most common ones are accuracy, that is the proportion of correct predictions among the total number of cases examined. So you can see here that the accuracy, the formula is true positives plus true negatives divided by n plus p, where n is negative and p is positive. So for you to see what TP, TN, N, and P means, you can go back to the matrix and see. So N is the negative and P is the positive. So what we're saying that accuracy is the true negatives plus the true positives. So the ones that we are good, that we're okay, we got it right, the predictions, divided by negative plus positive. So you can see the negative plus positive is everything, it's all the cases. So we are saying pretty much that the accuracy is how many did I got right out of everything. This is what the accuracy means. So it is the proportion of correct predictions among everything. The prediction, or positive predicted value, PPV, is the proportion of positive predictions that was actually correct. So that is the true positive divided by true positive plus false positive. So it's this thing here is the true positive divided by true positive plus 4 positive. So out of the ones that I said that are positive, how many of them are actually correct? The sensitivity or recall or true positive rate is the proportion of correct predictions among the positive instance. So I'm not looking at what was actually correct. Now I'm looking at all the positive instance. So the recall is actually the true positive divided by a true positive plus false negative. That is this part here. Now we're looking to reality, to what actually happened. So among all the people that actually had the disease, for example, how many of them I predicted correctly? And the F1 score is another common metric that is the harmonical mean of precision and recall. So you're going to have a mean there, which is good. We also mentioned that another evaluation metric is ROC curve. What is ROC curve? It's the ROC. ROC curve is a performance measurement for classification problems at various threshold settings. So you pretty much have a curve, this plot here, that what you're plotting is the true positive rate against the false positive rate, where the false positive rate is 1 minus the specificity. Or And from the ROC curve, we can get what we call the area under the curve. So for example, here, this is the curve. So this part here would be the area under the curve. And this can go from 0 to 1, because imagine that you're super awesome here. Your true positive rate is 1, your false positive rate here is also like it does this, kind of follows the X and Y there. And the area here is going to be 1, so that means that your predictions were 100% right. But if your ROC curve says it's 0, the area under the curve is 0, your model was 100% wrong. When your area under the curve is half, so it means that you're pretty much creating a line, a straight line here, and X and Y, you can see here it's called random classifier. It is random classifier because the probability of being right is half. So it's like throwing a coin. It's positive, it's negative, and it is what it is. So half, anything below half is definitely not good. So, and we want an AUC as closest to 1 as possible. I've mentioned before that the most common problem that we have here in classification is the class imbalance problem. What is this problem? This happens when the distribution of examples across the known classes is biased or skewed. So, and this distribution can have, I don't know, a very slight bias, but it can also have a severe bias. And what does that mean? It means, for example, you have a label of sick and not sick, and out of 1,000 users, 1,000 people, only one of them is sick. So your classification is highly unbalanced there, right? Because only one person is sick out of 1,000. So you have 999 that are negative versus one that's positive. And this is a problem because most of machine learning algorithms used for classifications, they are designed around the assumptions of an equal number of examples for each class. So the results, it's going to be models that have poor performance, poor predictive performance, specifically for this minority class. And usually the minority class is more important, right? So someone comes to us, they do a test for exam to know if they're sick or not, and we say that you're not, you're good to go. When they're actually sick, that's pretty bad, right? So in this case, the minority case was more important. So it is a lot easier for the model to just predict everything as not sick, for example. Hey, everything is negative. And then if you think about it, the accuracy of our model, if we go back here to accuracy, that's gonna be the sum of the ones that we are right divided by everything. By saying that everything is negative, we have 999 matches, so we are over the 1,000. So our accuracy is 0.9999. So that's amazing, right? You're gonna look at that, you're gonna say my model is great when it isn't. It's actually pretty bad because the thing that you actually wanted the most, you're not able to determine it was wrong classified. So that's why we need to look at other metrics that can tell us the prediction of the different classes, that can tell us how well the model performed for the different classes. So that's why we say that using accuracy as a performance metric is not recommended. So usually do look at raw curves, precision, recall, all those other metrics that are actually going to give you a balanced idea of how things are performing per classes. This is a much better metric. But we can try to overcome the class imbalance problem as well. We do have techniques that help us with that. So we can, for example, undersampling the majority class or oversampling the minority class. So assume that you have a larger database than one, but if you were undersampling the one with only one, you would have just one positive and one negative, for example. So you're undersampling the majority. And we have some of the techniques are called random undersampling and smooth oversampling, all of that can be used to help you with these types of problems. But let's start with the example now. The data set that we're going to use to perform this problem is the breast cancer from Wisconsin Breast Cancer Database. This data set can already be downloaded from one of our packages called MLBench. MLBench goes from ML Benchmark. It's a package that has some different data sets that you can use for ML problems. So this data is pretty small. It has only 699 observations and 11 variables. One of the variables is a character, and the other 9 are nominals, and we have one target class. So we can see here I'm removing the ID because we don't really need the ID. And we can see here, for example, some of the columns are the thickness, are the cell size, the shape, the margin, addition, I don't even know how to pronounce that, sorry. And the output is the class that can be either benign or malignant. So again, the class is benign or malignant. And we can actually see a summary of the data. So summary breast cancer. We can see that we have here, for example, the thickness that is more common is 1, followed by 3, followed by 5, followed by 3. The cell size, the most common one is 1. We have here the class, that's the which is gonna help us understand if the classification is imbalanced or not. So we have 458 benign cases and 241 malignant cases. So grouping by everything and counting so we can check the proportion. We have that 65% of the data is positive, so benign, and 35% of the data is malignant, so negative. This data, it's of course the balance would be 50-50, but we are rarely gonna find that in reality. But this is not a severe imbalanced case, it's just slightly imbalanced. So we are not going to apply any techniques to deal with class imbalance. For the data pre-processing, we can check if we have missing data by using the function any/na, and we do. So I count the number of rows before dropping the missing value. So I did just an n row function. We have 699, and if we use the drop na function, we can drop the missing values, and then we go to 683. So we did not have that many missing values on the data. And what I'm gonna do that in the data set, all the features are numeric. Even the ones that here were read as factors, they're actually numeric. And the only variable that I'm gonna leave as a factor is the class. That is our output variable. So you can see here that I'm gonna do that using the mutate at function from Dipler. So to use that function, I'm going to say at where I want to apply the transformation. I want to apply to variables. By doing minus class, I'm saying that I want to apply to all the variables from breast cancer with the exception, so removing the class variable. And the transformation that I want to apply is the S numeric. And now that we've done that, as I showed you with more details how to do the exploratory data analysis in the regression example, the summaries are the only exploratory data analysis that I'm gonna do for the classification example. But again, don't skip that step. I'm only skipping it because it's the example, and the goal here is to make you understand about the models and how to apply ML models to the data. So I'm not gonna do it for time, but you should definitely do it when doing this example. So the next step, what I'm gonna do is split the data between training and test. I'm gonna use the same split as I used before of 80-20. I'm setting the seed again for reproducibility, and whenever you try to do this at home, you can have the same results as I had. So I'm creating here the split. I call it B cancer split. As we saw in the regression, it's the same way. We use the initial split function, giving the data set and the proportion. Then to get the training set, we need to apply the training function to the split. And then we can see that we have the 80% represents 546 rows and 10 columns. To get the testing set, we apply the testing function to the split, and we are left with 137 rows and 10 columns. Now, modeling. What are we gonna do for modeling? I'll be using and comparing the results of two models, decision trees and support vector machines, or SVMs. So I'm doing this because a lot of times when trying to answer a machine learning model, we have a lot of models that can help us, and they're gonna have each one of them have their own strengths and weakness. So a lot of times we train a lot of models, and then we compare the performance of all those models, and we choose the one that can best understand our data, and that's how we choose the best model. So this is why I'm choosing two different models here to do these examples with you. Just to explain a little bit of the models that we're going to use here. First one is a decision tree. Decision trees are very common models used for classification and regression models, actually. And the nice thing about them is that they are very flexible and they are very easy to understand. So you can explain the results of a decision tree, which is very important, especially in this area of biostatistics. You want to be able to, I guess, tell people why you're saying that, if they're sick or not, for example. So uh, we have what is called root node, and we have decision nodes, leaf nodes. We have nodes and branches. And at each node, like these green things here, they are nodes. Uh, one of the features in our data set is going to be evaluated in order to split the observations in the training process, or to make a specific data point follow a certain path when making a prediction. So decision trees, they are built recursively, and they're going to be built by evaluating different features and using them at each node, so we can understand what features best splits our data. So you can see here that we have the root node. This is where we start the graph, and this is usually the variable that best splits the data. We have the intermediate nodes, like these green ones, that these nodes are variables. They're going to be evaluated, but they're not the final nodes that represents the predictions, not where the prediction is made. And then we have the leaf nodes that are the final nodes of the tree, and that's where we see the prediction with a category or a numerical value. And so, for example, I say that they are very easy to understand because you could have something like, do I want to go out tonight? And you can have root node as, is it raining? So if it's, so let's assume that no, it's not raining, and uh, is somewhere, I don't know, indoors. So if it's no, then I'm not going out. If it is yes, I can go out to some place indoors, then yeah, I will go out. But so if it's not raining, is it sunny? Is it windy? You can have these sorts of things here. So you can really see the decisions and how each of those decisions contribute to the final classification. The main uh, and the main advantages of using decision trees is that they are very easy to interpret. While other machine learning models, they are what we call black boxes. So black box means that you can't interpret, you don't know why the model is giving you the values that they are giving you. Decision trees, they not only can let you interpret the results, but they also give you a graphic, intuitive way of understanding what the algorithm does. So that's pretty positive for the model. And compared to other machine learning models, decision trees don't require a lot of data to train. And as you saw, we don't have that many data here in this example. So that's also a pretty good advantage for the decision tree. I said before they can be used for both classification and regression, and that is an ace to have on your possibilities. There are models that can help you. They're very simple and they are tolerant to missing values. I know I dropped the missing values, but to use a decision tree, I didn't need to because they accept that. So it's not going to have any problems with the model. But some of the disadvantages are that decision trees can be quite prone to overfitting, and they're very sensible to outliers. While you're creating this path, and unless you're trying to prune your tree, it can become pretty complex. The tree starts becoming very detailed, so you can start going from I don't know, if I'm wearing black, if I'm wearing blue and my socks is white, and I don't know, you can get really to tiny details. They're not really helpful to the classification of an observation, but they could be a part of the model, so they are prone to overfitting. And they are what we call a weak learner. So a single decision tree doesn't make great predictions. Ideally, we could have multiple trees combined and they make forests. And I don't know if you remember, but at the start, when I was talking about the possible models to help us with classification. One of them was a random forest, and that's exactly what it is. A random forest is are multiple trees combined. So this is a for a better model than a single decision tree. But for this example, we're gonna start simple with a decision tree. The other model that we are using to classify our observations is the SVM, or support vector machine. And what the SVM wants is to seek the balance between the margin of the decision boundary, where this is this dividing hyperplane. So you can see that this is creating the boundaries of what I'm going to classify as blue or as red. And we also want we want the balance of that with the number of classified points that I'm willing to accept. So it means that how many points, how many reds and blues I'm willing to misclassify, and where the margin's gonna be. How do I maximize that? How do I create this balance? This is the whole idea in summary of the SVM. And it is a very powerful model, very common model, and that's why I'm also used very versatile. It works very well in high dimensional space. So when you have a lot of variables, a lot of features to work with. But one of the disadvantages is that it does not provide a directly probability. So you need to there is a more complex way of getting the prediction, but of course the algorithms in R then simplify everything for us. So we can use it just like any other model. So we can start actually applying the model to the data. So we're still going to use parsnip. If you remember, we need to first tell what kind of model we're going to work with. So for the decision tree, the parsnip says it's decision tree. And for the SVM, we're going to use the linear type. So I'm going to use SVM linear function. To set the engine and mode, we still use the same functions from before, and we need to define the engines that we actually want. The mode, now before it was regression, now it's classification. For the decision tree, we're going to use rparts from the rparts package. So you need to have that package installed to be able to use this engine. Remember that for our linear regression, we used the LM that was from base R, so we didn't need to install anything. But in here, you need to do install.packages rpart. And the same for the SVM. We are going to use the linear engine from the package with the same name. So install both of those packages. And we can see that then we create those models the same way we created linear regression, but setting the new engines and the new models. To fit the model to the data, then we use the function fit that we need to give then the parsnip object, that is the tree model for the tree, and SVM model for the SVM. We need to give the formula. In this case, class is the outcome, and our x variables are going to be all of the variables that we have. So that's why I'm using the dot. And the data set that we're using, remember, we need to fit the model to the training set. So I'm fitting it to the train. So when we see, for example, the SVM, the estimates of the model, we have here the values. You can see the same for the decision tree. If you want, you can view the model properties. But then what we actually want to do, so you can see that it's the same recipe as the regression, but now with another problem in mind, now with the classification in mind. So now once you train the model, you predict on the test set. So to do that, we use the predict function. Again, I'm going to bind all the columns together, so have everything in different data sets. I'm going to do the same for the tree. So I'm creating a data set for the tree, and I'm creating a data frame for the SVM. And you can see here the first two observations for both. So it says that the prediction is benign and the prediction of the second observation is malignant. And we have the same predictions actually for SVM. So we are predicting the same for those two observations. But as you can see, I'm not showing you the class, so suspense for us to see the actual evaluation metrics next. So to evaluate the models, what I'm doing is I'm using the function confusion matrix from the library Caret. So install that package as well to have access to this function. And what I need to pass, this is for the decision tree, and this is the result for the SVM. What I need to pass for them is the predictive class that it's called .pred underscore class, and I need to pass the reality, that is the class column from our data frame. So you can see here that I'm passing the exact same things. I'm using tidy just to have a result in a tidy way that I can see. I'm filtering here just to a few of the metrics because they're gonna give you a lot of different metrics. You can select the ones you want. You can see all of them, so you can start getting used to the different performance metrics that you can have access to on a classification problem. And I'm just selecting the term, that's the name that they give for the actual performance metric, the class, that is the class, if it's benign or malignant, and that actually represents the reference. So it's saying that it's checking, it's using benign as reference. That would be the ones or the zeros, and the estimate. And that is the actual performance metric. So we can see here that the decision tree had an accuracy of 94.9 and the SVM 95.6. But we know that accuracy is not what we want, right? The classes were not perfectly balanced, so we are more interested in the other classes and the other performance metrics. So specificity, we have 0.95 versus 0.91, precision 0.98 versus 0.96, recall 0.95 versus 0.98, and F1 0.96 versus 0.97. They're both very, very good models. You can choose the best model now based on what you want to control the most. Do I want to control the false positives or the false negatives? Type 1 error, type 2 error, but both models are above 90%, above 95% most of the time. So the model trains very well, and this is the evaluation of the model on the test. So we actually managed to generate on unseen data in a very, very, very good way. These models are great. And this is it. This is how you determine and how you apply a classification type of model to a classification type of problem. Now we can start thinking about unsupervised learning, the second type of machine learning types of problems. Unsupervised learning. So we've been talking about supervised learning and their types of problems. And what characterizes supervised learning types of problem is the existence of a label. So the existence of the actual real classification value of the observation. In an unsupervised learning environment, it is called unsupervised because we don't have a label. We don't have the truth. So the idea is that the algorithm is going to learn patterns from unlabeled data and be able to cluster to understand how those patterns behave, how I can separate data. So that is the main difference of supervised and unsupervised. So some common tests are clustering. That's when you group unlabeled data based on their similarities or differences. So just like the image there, this is a common clustering example. So I have triangles, circles, uh, whatever the other thing is, and then you apply the algorithm and you can actually say, okay, the triangles are here, the pink and blue shapes are another type of data, and the circles are a different type of data. So this is what you're doing there, and an example of an algorithm that can help us is k-means. Another test that we can do is dimensionality reduction. So we reduce the number of features while also preserving the integrity of the data set as much as possible. So one of the common algorithms is principal component analysis, or PCA. But we can have challenges when allowing machines learning models that will execute without any human intervention. And we have a lot of computational complexity due to a high volume of data. And so let's start actually diving deeper to some of the models that we're going to see here. So clustering is the first type of problem that we are going to be seeing. Clustering is the probably the most important unsupervised learning problem, and probably also the most common one. So it involves discovering groups in the data. So unlike supervised learning, clustering algorithms, they're gonna interpret the input data, and based on that, they're gonna find natural groups or clusters in the feature space. So clusters are going to be a collection of objects, a collection of observations. There are similar between them, so they're similar between the people, between the observations, and within the same cluster, but they are going to be dissimilar to the observation belonging to other clusters. So given a set of points with some distance between them, we can group the points into clusters such that the internal or the within the cluster distance, so the observations that belong to the same group, should be small. So that means that members of the same cluster are close or similar to each other. But the external distance, or the intra-cluster distance, should be large, and that means that members of different clusters are dissimilar, are far from each other. And so one of the very, very important points here, so we're going to see if people are close or if people are far from each other, if they're similar or dissimilar. So it's very important to determine how we are going to calculate how close two observations are. So the distance metric here is extremely important. So you need to define a distance or proximity metric for 2 points. And a good proximity metric is very applicant dependent. So you cannot say I'm always going to use, for example, Euclidean distance or Jacquard distance. That will change based on the problem you're trying to solve. So we can define a distance as how similar or dissimilar two points are. Similarities are going to be large if two people are alike, and the dissimilarity or distance is going to be small if two observations are alike, if two observations are similar. So common metrics: Euclidean, Mahalanob's, Jacquard, Manhattan distance, cosine distance. You have a lot of distance metrics that are going to be, again, very application dependent. The steps to solve any machine learning problem are going to be the same no matter if you're in a supervised or an unsupervised environment. So we're going to keep with the same steps that we've been following so far. To do the clustering example, it's going to be very similar. The difference is that we don't need to predict anything, right? We don't have the reality. So we don't have anything to compare to. What we want is to see if there are groups in our data. So the only difference here is that the prediction step won't exist. And with that, the evaluation one. So to do this example, we are going to use the built-in R dataset called USA arrests. This dataset contains in statistics and arrests per 100,000 residents for assault, murder, and rape in each of the 50 US states in 1973. It also includes the percent of the population living in urban areas. So the libraries that we need to do clustering is cluster and factoextra. So you need to install and load those libraries before proceeding with the example. So as I said, it's a built-in library, so you can just call that. I'm just giving a different name, but you don't need to. You can just keep calling the USA arrest if you prefer. So I'm checking here, I'm doing a glimpse of the data so I can see a little bit of the data. As I mentioned, there are four columns: murder, assault, the urban population, and rape. Again, we don't have a label, we don't have an outcome, so that's what we're gonna have to, I guess, figure it out. So the data processing, for the data processes, first I'm going to check if we have NAs and remove them if they are present in the data, which they are not. And you can check using the any NA function. And we don't want the algorithm to depend on any arbitrary variable unit. So we don't want the algorithm to be to have scaling problems. So remember when we mentioned we might need to standardize to apply min max normalization. This is what we are gonna do here. We are gonna scale our data, our variables. I'm gonna use the function scale that it's normalizing to a distribution. Sorry. And we can see here how things are now. We definitely don't have those, for example, assault, there were big numbers, murder, there were smaller numbers, good. But in here, they are all around the same range. So that's good. We can do a distance matrix. We can see the distance we can visualize that by using the functions getDist and fvisDist from the factoextra. Factoextra is a package that helps us with the visualization side of things. With the getDist, you can compute the distance matrix between the rows. And we are going to use Euclidean. That's the default. They have different distance metrics as part of that function. You can go and change the distance to see how that changes the final clustering of the variables, of the observations. Again, we're calculating the distance between the rows because we calculate the distance between the observations. We want to see how the observations are similar and unsimilar to each other. And we use the fvisDist to actually visualize this distance. So we can see here that the distance is going from 0 to 6 on an Euclidean metric. And we have here those states here are more similar, they're more distant, so they're more different, but smaller distance like 0, the closer to 0, the more similar those places are. So we have here those values here, and the distance of, I don't know, Alabama with Alabama is 0, right? Because it's u, the distance of u to u. it's zero. So that's why this line here is pretty red. That represents zero. So to do this, to the model that we're gonna apply, we're gonna use k-means. K-means is the most commonly used unsupervised machine learning algorithm for partitioning a given data set into a set of k groups. That's why it's called k-means, for k groups. So in k-means clustering, each cluster is represented by its center or centroid that corresponds to the mean points assigned to the cluster. So we're gonna determine the k clusters, and again they are all gonna have a centroid, but what is the optimal number of clusters? If I don't know how many clusters, how many groups I have in my data because I don't have a label, how do I choose that number of clusters? Because if I put it has to be greater than 1, right? If I put 2, the model is going to give you 2 clusters. If you put 3, the model is going to give you 3 clusters. You can choose however many clusters you want, however many groups you want. But that doesn't mean that that is the optimal number of clusters. So as the clusters is user specified, we have ways, we have methods to determine the optimal number of clusters. These methods can be, one of them is called elbow method. It comes from this. And why? Because you need to minimize the total intra-cluster variation. So you have functions that are gonna help you with that. All of them have functions. You don't need to implement any of that by on the scratch. All of them have a function. So you're gonna see why it's called elbow method on the next page because it has a chart of it. We also have another method called silhouette method that it's measuring the quality of your cluster, so it's determining how well each object lies within the cluster. If you have a high average silhouette, that indicates a good clustering because it means that things are pretty well in there. And you also have what is called gap statistics. That this approach can be used to any clustering method, and it's going to compare the intra-cluster variation for different values of k, for different values of clusters, with the expected values under the new reference distribution of the table. Again, all of them have functions that were already loaded. For the elbow and the silhouette method, the function is the same, is the FVS and B cluster. What changes is the method. For the elbow, the method is WSS, and for the, because it means within cluster sum of square. For the silhouette, the method is silhouette, and the gap statistics has a different function that pretty much says gap stat, and you need to use a class gap. So let's see the functions and why we called, for example, the elbow one elbow. So I'm using this patchwork library just so I can put all the charts together. I'm gluing all the charts in one so you can see and compare them. Again, I'm setting the seeds so you can have the same values as I'm showing here. I'm calculating the elbow method, as I said, with the FB and B cluster. You need to give the data, that is the US arrests scaled. I'm running the K. You need to generate the k-means that I'll show you later what it is. Let's see, here it is, the k-means. I'm using, so it comes from this, it's the same function here. I'm just saying that I'm generating a k-means function here. It's just it doesn't look like a function, right? Because it doesn't have the bracket or anything, but that's what it is. And the method is the WSS. We do the same for the silhouette, but the method is silhouette, and we do the gap stats. As I said, it runs for different case, so I need to give, I don't know, a max of 10 cluster. That's what I want. And this is, we can plot later. So if we can see, this is called, the first one here is the elbow method. You can see we call elbow because it kind of looks like an elbow, this part here. And we say that the optimal number of clusters is where the elbow actually is. So we can see that the elbow, before the biggest drop until it kind of things kind of normalize, I would say here that it's like 4. Then we have here that the optimal number of clusters in the silhouette is the highest one, that is 2. And in here we have that the optimal number of clusters for the gap statistics is 3. So they're not agreeing, but they're pretty okay. Like we can even say here that the elbow one says it's 3, actually not 4, because this drop here is not very big. So 1, 2, 3. This is the biggest drop, the last biggest drop that we have. So you can stick with 3 here, 3 and 2. But with most of them suggesting 3, we are gonna use that as the optimal cluster. So again, setting the seed as 1, 2, 3, and then the function to calculate k-means is called k-means. So we give the data set, that is the USRS scaled. We give the number of clusters, that's 3, and this is just the start. I'm saying that it's 25, and we can print the k-mean results. So we have here that then what we're going to have is that each of the observations, so each of the states are going to be assigned to one of the 3 clusters. And this method gives you kind of a summary of the cluster as well. So we can see here that cluster 1, it has it has a higher assault and murder and rape rates, but the urban population is not that dense. On the other side, we have here, for example, the 3 that we seem to be pretty okay in everything. It's more difficult to see with the scale values, but it's just so you can have an idea of the means of murder, assault, urban population, and rape for each of the clusters. So the interesting part is to actually visualize the cluster, so we can plot there using FV's cluster function. So we plot the k-means. We have here the data. Oops. Yeah, we have here the data, the scale, and then we are plotting already with the names, what they represent. So we can see here that cluster 1 has California, Nevada, Colorado, New York, Texas, which they seem like big places, right? California, New York, they're pretty big places, but it also has Alaska, so it's not necessarily, related to the population density. So for the second cluster, the green one, we have other states like South Dakota, Montana, Kentucky. And the third cluster, we can see that we have Arkansas, Wyoming, Virginia, Ohio. And one interesting thing is that they are very well separated, right? We can clearly say that there is, okay, this is 1 cluster, 2 clusters, and 3 clusters. So there is a distance between them, and they seem to be pretty close together within them. So 3 seems to be visually a very good cluster number. And the final step then, so you visualize, you create the cluster. What is the final step? is to actually extract the clusters and add that to our initial data so we can have some descriptive analysis. We can do some descriptive statistics at a cluster level. So in here, I'm just going to do a simple average, but you can do more with that if you want. So we can see that cluster 1 actually has a lot of, it has the highest murders, the highest salts, kind of an average between those three, right? It's in the middle of the urban population, and it also has the worst rape mean values here. Cluster 2, on the other hand, it's doesn't it clearly it's the one that has the least amount of murders. It's also the one that has the least amount of assaults. The urban population's not that populated, and the rape is also the one with the least number of rape, but it's pretty high as well. And the murder, we have that this one is between the other two. It has assault is also between the other two. It's kind of an, but the rape one is it's also between the other two. The only difference, there's no difference. It's actually the cluster 3. It's kind of the mid-level between 1 and 3. So you can do more interesting statistical analysis to better understand the clusters, the observations within those clusters. And that's how you finish a clustering type of problem. Well, now we can briefly talk about principal components analysis. So this is the other common type of problem that you can solve when you're dealing with unsupervised learning problems. So PCA is an unsupervised machine learning technique that seeks to find principal components, and that means linear combinations of the original predictors that will explain a large portion of the variation in a data set. And what does that mean? It means that the original predictions are your features. So you have your a lot of variables, a lot of features, and then you want to do kind of linear combinations between them so you can understand how many out of those linear combinations how many of them do you need to be able to explain most of the variation in the data using the least amount of principal components you can have. So the goal here really is to explain most of the variability of a data set with fewer variables than the original data. Because of that, as we're having these linear combinations, these fewer variables, it is very difficult to interpret the features resultant from PCA. So you don't really know, you don't really have the means to explain what they mean, but it does make a lot of the analysis easier. So if you don't need the explainability, it can be pretty helpful. So to do the example, we're going to work with the dataset FAT available in the Faraway library. So you need to download that library to have access to the data. And this dataset contains 18 physical measurements. So you can see here I'm attaching the FAT dataset, and we can see the glimpse. We have 18 columns. 18 columns, it's not that many, but this is just an example, so that's why I'm gonna use this data. But 18 columns is pretty doable without needing to reduce the to reduce the uh, original variables from the data set. And we have 252 rows. So you can see here that we have, for example, density, age, weight, height, a lot of physical measurements. So the pre-processing here, PCA, is influenced by the magnitude of each variable. It is influenced a lot. So before we do anything, we need to scale the variables. We need to do that, or we're gonna have problems here. The variables are not really maybe as impactful as the PCA is gonna show us. So if you can see, I'm using the function apply. I'm saying I'm passing the data set, fat2 means columns, var means that I'm applying variance. So I am dividing by the variance. I'm sorry, I'm not dividing, I'm checking the variance of the data. We can see here that we have a lot of variance. We can see that the variance of this one is like 60, but others is 5. So this one, the wrist, probably that circumference of the wrist, it's probably 0.87 the variance. So it's pretty different, and that's why we need to scale the data set. And PCA works best with numerical data, so if you're working with categorical features, you need to dumbify. That means hot encode your data before working with that. So as I said, we need to scale the data, we need to normalize the values there. So the functions that we work with in PCA, one of them is called prcomp. And you can set 2 arguments. You need to give the data and you can set 2 arguments, but those arguments are center and scale. So you don't need to normalize the data before applying the PCA because the function lets you do that all in one. But what it's doing behind the curtains is that it's going to center and scale your data first and then apply the methodology. So what I'm doing here is saying center equals true and scale equals true. So it means that I'm applying the Z normalization. I'm removing the average, the mean, and dividing by the standard deviation. So it's a 0, 1 normal distribution. You can see here I'm displaying the summary of the PCA. So as we have 18 features, we have 18 principal components, and each of those principal components, are gonna explain a percentage of the total variation of the data. And remember, we want to maximize the variation that we can explain with those principal components, but using fewer variables. So you can see here that the first principal component explains 59.79% of the total variation of the data. So this means that a little bit more than half of the information that this data set has can be encapsulated, can be explained by just this first principal component. When we get the second principal component, we see that the second principal component by itself explains 15% of the variability of the data, but alongside the first and the second, so this is a cumulative sum, we have 75% of the data already explained by only 2 components. And you can see that as it's cumulative, you get to 1, but you can see here that some of the principal components, they're not adding that much information anymore. So we're in 99965 to 99999. So they are not very helpful. And this one here then explaining the last principal component explaining pretty much nothing of the data. So this is how you can determine how many principal components you are gonna choose. So for some applications, you might need to explain, I don't know, at least 90% of the variability in the data set. So you would say I need 6 principal components. For others, you might need even more. You might need, I don't know, more than 95. So you need 8. You might need at least 80%. So you need 3. So that all depends on the context you are inserted into. I'm just going to choose 2 because it explains 75 is enough for the example. And the important thing here is to be able to visualize, to plot those principal components as well. So we can plot using the library ggbyplot. This is from GitHub. So to install this library, you need to use the install GitHub function from the DevTools package. This is how you install something using DevTools. This is the GitHub user and the project from GitHub. And so then once you install, you can actually call the package and use the function. So you can see here all the data points, all the observations are here. As I'm choosing just two PCAs, that's how I can plot because it has only two coordinates. So this is the first one. The second one, it tells you how much is explaining by. And if you see those red arrows here, they are representing each of our features. So this way we can have an idea of how the principal components relate to the original variables. So once you have the principal components that you want, that you need, you can do the analysis that you might want to from there using those principal components. Again, remembering that they don't, their explainability, it's gonna be more difficult to understand since they're linear combinations of everything else. But from this chart, you can try to understand how they related to the components. So age, density, they seem to be, density seems to be a high PC2, linked to a higher PC2 and a lower PC1. Age, on the other hand, seems to be more linked only to PC2, and that's how kind of you try to understand what's happening. But this is how we work with PCA. And this is the power of PCA to be able to do the analysis to get useful results from the analysis without having to use all the variables you have available for you. Because if you're working on like genetics, that you're gonna have thousands, hundreds of thousands of variables, it's going to be very complex and difficult to run a model with all that, so being able to reduce the dimensionality of the data is pretty important. You can also do that to compress images. This is a very common old algorithm for compressing images as well. So a lot of things can be done with this technique. And finally, we can talk very, very briefly about reinforcement learning. So reinforcement learning is used a lot in games, as I mentioned before. And why? Because this kind of has a gaming idea behind. So you have an agent that you train that agent, and that agent's gonna interact with environment. So it's gonna play around. And the agent is gonna arrive at different scenarios, and those scenarios we call states. And the agent arrived at these states by performing actions, and those actions lead to rewards. So you can kind of think of us when we are learning as kids. So I don't know, you you see fire and say, maybe I want to put my hand there, and then you go and do it and it hurts, and so you know that putting your hand on fire hurts and that's bad and you don't want that. That's not a reward, that's not a good reward. But I don't know, if you like chocolate and you eat chocolate, you like it, that's a good reward. It was good for you. So this is kind of how we learn things as humans as well. So the whole purpose of the agent is that it wants to maximize the total reward across an episode. So if you think of as a game, so you might have, I don't know, a rat on a maze, and you have small pieces of cheese and big pieces of cheese. And once the rat goes, it learns how to, I don't know, how to, by going left to going right, it learns how to get to the cheese, and that's uh, reward. The reward is positive. It likes it keeps going there. It learned how to go there. But of course, in an episode, it's gonna be everything that happens between the first state and the last or terminal state within the environment. So if you're playing a game, it's game over, the episode ended. And if you start another game, then you are in another episode until you either win, so yay, or you lose, right? So this is the end of the uh, episode. In reinforcement, we reinforce the agent also to learn the best action by experience. And this is what we call strategy or policy. So if we go back to the rat in a maze example, if you if the rat always goes to the small piece of cheese, uh, it's gonna get a reward, but it will know that there are bigger pieces of cheese on the maze. So you need to do what we call exploration and exploitation. So you need to exploit what you already know, but you also need to be free to explore because maybe you're gonna find something better, something that will increase your reward. And one of the properties here is that we use here is a Markov property, and that means that the state that you are only relies on the previous state, and that's how it goes. And so the next action depends on the action you're now. So if you went forward now, it doesn't matter that you went forward. If you went forward as well before, now what matters is from here, what can I do next? And this is just, again, as I said, a very briefly introduction to reinforcement learning. It's very interesting to play around. There are some engines that are open that you can play around. A very famous one is Open AI from Gene, if I'm not mistaken. And you can just see what you can do and play with some games and see if the computer can beat you in some games. To finish, we're gonna talk about deep learning. So deep learning is a subfield of machine learning. And we saw on that first image from one of my first slides, we saw that we had AI as the main one, the biggest one, and then machine learning is a part of AI, and then deep learning is a part of machine learning. And what we have here is that the algorithms in deep learning, they are inspired by the structure and function of the brain. So that's why we call a lot of the models here, they are called artificial neural networks, or just NN, neural network. So for the old generation of learning models, they kind of plateaued. We kind of know things, and but deep learning is a class of algorithms that it's scalable. The performance just gets better and better the more data you feed them. So the old algorithms, even though you have, look at this chart here, even though if you have a lot of data, it plateaus. It's not gonna get any better. You reached a performance, and that's it. But with deep learning, if you keep feeding example, keep feeding observations, it can keep getting better and better and better. So that's the good thing of deep learning. They're very powerful, but the problem is you need a lot of data, and it's really a lot of data, which can be difficult to find depending on the context you're inserted. So this is just a brief explanation on deep learning as well. If you're interested, if you want to know more about it, uh, I hope this introduction can help you to look for that in the future. This is just to finish. I have some reference here that I used, the CSV for the first data set that was in GitHub. I used a lot the Elements of Statistical Learning. That's a pretty good book from Tibishirani. I recommend reading that book if you are interested in it. And I also use another book called Machine Learning, a probabilistic perspective. So I hope you enjoyed the class and that you learn a lot from it. Thank you very much. Bye bye.